And I want to talk about the Pamela anomaly. And what I want to present is, on one hand, the simplest, and the other hand, the most unorthodox explanation for the Pamela anomaly. It's the simplest because it's coming, according to this idea, the excess positons of Pamela are coming simply from galactica, from supernova, which is the standard source for cosmic rays. It's the most unorthodox because, unlike practically everybody else in the field, we simply say that there is no excess. There is nothing to be excited about. So from this point of view, I feel a little bit embarrassed. It's like somebody, party breaker, because, the guy who called the police and said that there was too much noise. And so, because it would be beautiful, wonderful if this was, we discovered the dark matter, or Pamela discovered dark matter, or a new source of, new astrophysical source. But we are just saying that this is not it. Now, let me begin by a short introduction of what is Pamela. So if you do the following exercise, you go to Google and you do Google search images of Pamela, you find this, and this is for about the first 99,000 images.
And actually she's Swedish.
Actually, if you don't believe me, this is the homepage of somebody. What physicists think about Pamela or something like this. Anyway, let's leave this slide and go back to but we are slightly more serious. So if you look more carefully, you manage to find this and even this. So Pamela is a cosmic ray detector with ability to distinguish between positons and antiprotons, and electrons and protons also. And this is very important feature, the ability to distinguish between positons and antiprotons, because the ratio of positons to antiprotons is very small. It's about 1 to 1,000. So so the ability here is critical, because if you are mixing somehow antiprotons for positons, sorry, protons to, not antiprotons, if you're mixing protons with positons, then the whole effect goes.
So it's 1 to 1,000 watt energy.
1 to 1,000 positrons per proton.
What
the same energy. The same energy.
Entire energy band?
At the energy that we are talking about, tens of GeVs. So what is the Pamela anomaly? This is the ratio of positrons to total of electrons and positrons. So basically it's positrons to electrons, because this is a small fraction. And these are the observations. They go down, and then they reach at around 10 eV minimum, and then they begin to increase. This increase in the ratio was seen already in previous experiments, but this is the first time that it is statistically significant, and it goes up to further, to higher energies, where it is seen very clearly. So this is the basic result. The positron ratio goes down, reaches a minimum around 10 GeV, and then it goes up. The fraction of positrons. And this is compared with theoretical models, which you see here. And the theoretical models, the theoretical model, which is basically based on a calculation by Stinkalenko and Strong, show that this ratio should go down, and I'll explain in a second why it should go down. And it is going up by a factor of about 2 compared to what it should go up. So the interpretation The common interpretation, and by the way, this was first announced here in Sweden in a conference about 10 months ago. The interpretation was that there is a new source of electron and positron that become dominant at about positrons, new source of positrons that becomes dominant at 10 GeV, and while the regular positrons continue to decay, this new source is increasing, and we have to explain what is this new source of positrons. Now, the most common interpretation, and there are more than 100 articles suggesting it, is that it's decay of exciting particles. And if such particles, if you have such high energy dark matter particle, it decays, among other things it produces positrons, and this is the new source of positron that we are talking about. And this is interpreted as detection of dark matter. This was in Science News, and if you don't know, this is how dark matter looks like. This is from the article.
But
yes,
this interpretation does not require also production of antiprotons in such a way it will be observed.
This requires also production of antiprotons. And the same experiment, Pamela, I'll get to it at the end, does not show excess of antiprotons. So this is a problem. There are other problems with this interpretation. The biggest problem is that we all know what is the expected cross-section for dark matter annihilation, and if you use the standard ideas, what was expected earlier for dark matter annihilation, I'm not going to see it, so you can check. If you use the standard interpretation and plug the numbers, you get that the fluxes that you see here are about a factor of 1,000 weaker than what is expected. So this is why there is so much work on the dark matter scenario, because the standard dark matter scenario does not work.
That was not known to all the. That was not known to all the 100 people that wrote.
No,
papers.
it's known. So that's why all these 100 people are trying to find an unorthodox models for standard for dark matter. So you have to. There is a leptophilic, yes, not leptophobic, but leptophilic dark matter. So it prefers to decay to leptons. In addition, this dark matter, there are two ways to enhance the cross section. One is what is called the Sommerfeld effect, which is an effect which suggests that at very low energies, the interaction goes faster at very low velocities than what just the simple extrapolation. This gives you a factor of about up to 20 in usual conditions, so, but it's not enough. And on top of this, you put now an astrophysical concentration. Dark matter is not uniformly distributed in the galaxy. It is distributed in clumps. And if it is distributed in clumps, then the annihilation goes like n squared. This can give you another factor of 20 to 50. So altogether, there are models. That's why there are 100 papers. If this was the standard model, you didn't need 100 papers. You needed one. But since there is no simple explanation, there are all kinds of attempts to work out how you can get this with dark matter. On the other hand, astrophysicists are not lazy also, and there are other suggestions are of astrophysical sources of pairs. The most common is the idea of pulsars. To be fair, the idea that pulsars produce pairs of cosmic rays in these energies is actually an older idea. It was proposed before these observations. The only problem with this idea is that there is no direct evidence that this is really taking place and with the right energies. So you invoke a new source of source, and there's also quite a lot of work on how pulsars, what is the distribution of pulsars, and how it should be done in order that pulsars can explain this. But like particle physicists or physicists are not just left with just one model, so they're also suggesting that GRBs, magnetars, and a few other sources can produce it. There is also a suggestion now that supernova remnants, in supernova remnants there is a new process that secondary collisions within the supernova remnants produce not just supernova remnants, of course, contain mostly protons and electrons, but now the suggestion is that collision between cosmic rays within the remnant or very nearby to between the remnant and nearby matter produces pairs. So this is another suggestion. But so the standard solution is that dark matter, it requires new physics. I want to stress it requires new physics twice. First, dark matter is sort of new physics, but moreover, it is not the standard dark matter, it's a new special dark matter. And or pulsars, which is some sort of new astrophysics or some other astrophysics. So the question that you ask, is there a new and simpler solution? And the new and simpler solution is that is supernova. Supernova are the canonical sources of cosmic rays. The mechanism exists, first order diffusive shock acceleration, and already in '63, Ginsburg and Sirovatsky suggested the energy sort of agrees with the cosmic ray density and lifetime if the supernova produce between 3 and 10% cosmic rays. So traditionally, if you open a textbook, it will suggest that low energy cosmic rays, at least up to the knee, are produced by supernova remnant. So this is something completely standard. And actually, observation of synchrotron from supernova reveal efficient electron acceleration. So this is, for example, the same picture. This is so the high energy band here, the blue band, is actually synchrotron line, which explain now the point of the whole talk, of the whole idea here, is that the supernova are not uniformly distributed. The supernova, as we know, are concentrated in the spiral arm. At least type 2 supernova are concentrated in spiral arm, but also some fraction of type 1 supernova also follow star formation. So both of these types should be concentrated in spiral arms when we have a star formation. This is a distant galaxy where you can see concentration of supernova remnant in spiral arms, but this is the synchrotron emission in radio in our galaxy by relativistic electrons. You can see here very clearly the spiral arm structure. So it is not surprising that this is the case. There is also some indirect evidence from which I won't get into. There's also some indirect evidence from meteorites and from fossils that suggest that there is the cosmic ray flux oscillate on a time scale of hundreds of millions of years, and this time scale is compatible with the motion of the Earth or the Sun and the Earth in the galaxy, and the fact that we're getting closer and farther from spiral arms. So my colleague with whom we did this work, Nir Shaviv, has devoted a lot of work to this for much more important reason. He claims that this has to do with the influence of cosmic rays on climate on Earth, and it has to do with changes in climate, but I won't go into this. So this is why you see the temperature as reflecting this fluctuation, but I won't go into this. This is a subject of completely different discussion.
Just out of curiosity, if you already mentioned it, what are the evidence that you put for the excess of cosmic rays, hundreds of millions years ago?
Well, one evidence is if you believe this idea that the cosmic rays influence, the flux of cosmic ray influence the clouds on Earth, the level of clouds, and hence the level of precipitation, then this fluctuation in temperature is one indication of this. And the second thing is when you look at meteorites, you see different ratios of isotopes. And these different ratios of isotopes give you this indication for fluctuation. But it's really not my field, so I will not try to explain it.
The present time is near the. I don't quite understand that.
What?
The present time is near to the maximum.
We are at present at about 1 kiloparsec, and we are moving away from nearest galactic hour. So so right now the flux of cosmic rays is going down compared to what is expected. Now the idea why supernovas should be in spiral arms is very simple. You have a cloud, a molecular cloud, and the molecular cloud passes through the enhancement of the spiral arm. This passage leads to disturbance in the cloud, and the disturbance produces trigger star formation, and this triggers supernova, which actually, if you take into account the time that it takes, they don't happen exactly in the spiral arm. They trail into the spiral arm by a few tenths of parsecs, but it's not significant compared to what we are interested in. Okay, so why it is important? Why is this distance important? Protons and electrons are primary cosmic rays. They are produced in the supernova remnants. Positrons are secondary. And positrons are produced, according to the standard model, by collisions of protons, cosmic ray protons, with protons in the ISM. And these collisions produce spirals and so on, and also positrons. So the positrons are secondary. Now, both the positrons and the electrons cool as they propagate through the galaxy. Now, here it goes like this. This is the spectrum of the positrons and the electrons at the source. Now, the positrons and electrons diffuse in the galaxy and escape. They escape when they reach the scale height of about 1 kiloparsec, when the magnetic fields are too weak to hold them, and they escape. This process of diffusion and escape reduces and since the diffusion coefficient depend on the energy, so since the diffusion coefficient depend on the energy with some factor here, this reduces the original slope, which is e to the minus alpha, the original slope, to e to the minus alpha plus beta, e to the minus alpha minus beta. So if you begin with e to the minus alpha, the observed slope is e to the minus alpha minus beta because of the diffusion. Now, the secondaries, the positrons, which are secondaries, suffer diffusion twice. First, the source, so the observed spectrum is expected to be e to the minus alpha minus beta. Alpha is the spectrum at the source, beta is the diffusion coefficient. Now, the secondaries, like the positrons, suffer diffusion twice. First, the source diffuse, the protons diffuse, and then they diffuse and escape. So this is why the spectrum, sorry, this is now on the spectrum. So the spectrum should be proportional to e to the minus alpha, while the spectrum of the secondaries should be proportional to e to the minus alpha minus 2 beta. And so you expect that the spectrum of the secondaries will be steeper than the spectrum of the primaries. And this is the E plus spectrum in the galaxy because of the faster diffusion. Now, if you compare this E plus to the electron spectrum, if you compare the secondary to the primaries, because of the second diffusion, you see that you expect the positron flux to go down and to be lower with energy than the electron flux. And this is why the standard model suggests that this should be the ratio. So this is the reason why if you divide this by this is exactly the reason why the standard model suggests that you have here a slope of e to the minus beta, and it should go down with energy. So this is the standard prediction why of the standard model, and the observation are now go like this. So there is a problem, there is excess here. So this is the basic problem. Now, but you have to take a second effect into account. And the second effect that you have to take into account is cooling. Along the way, when the cosmic ray the leptons diffuse, they cool. This is the cooling equation. And the cooling is because of synchrotron losses and inverse Compton losses. And this cooling adds to the electron and to the positron additional steepening of the spectrum. So we have to take into account of this cooling. And if we take into account of this cooling, we can ask the following question. What is the typical distance that an electron can pass before it has that a typical electron will pass before it will have enough time to reach us? So we equate and ask at which energy and which distance the diffusion time is equal to the cooling time. And we find that for about 20 GeV, 1 kiloparsec, and 1 kiloparsec, the diffusion time will be equal to the cooling time. This means that around 20 GeV, if the source is now not uniform but at 1 kiloparsec, you will begin to lose electrons because of cooling instead of before they reach you.
Wait, sorry, this estimate depends on the magnetic field, right?
No, not so much, because you have here, this is the inverse Compton on the CMB. It's a robust thing, so there is dependent on magnetic field, but this is the robust value which don't have to worry so much about.
And when you refer to electron energy, that's the observed electron energy, because the source gives you some spectrum, so you can go to higher energies.
The source gives you some spectrum, and in addition to this, whatever the source gives you, there is diffusion. In addition to this, there is a cooling. You have to take into account all three effects.
No, that's fine. But what I'm saying is that if you look at energies in the source which are higher, right?
Yes.
I mean, by the time they get us, how to say? It will take longer time to cool to this energy that we are observing, right?
It's worse than this. The cooling is very, very efficient. So if you look at energies significantly higher than this energy, and if the source is at 1 kiloparsec, you simply won't see anything.
Exponential cutoff. It's just the cutoff.
There is a cutoff. This introduces a cutoff. This cutoff is exponential.
We'll discuss it later. I'm not sure that's it.
The cooling introduces.
Cooling is cooling, right?
If
Start with some
the
energy and you
source-
lose energy as you
If the
property.
source is at a given distance, this it's supposed for a second that we have a source at 1 kiloparsec.
Yeah.
Then if the source is at 1 kiloparsec in a typical time that the diffusion is such, it's for 20 to 20 GeV, this means that above 20 GeV you will get exponential separation of the contribution of the beyond the diffusion, which is much stronger than the diffusion.
Not exactly exponential because it depends on you produce them all over the place. So some.
I'm talking about if you produce them uniformly, you don't get an exponential cutoff. But if the source is at one distance, if you put the source at 1 kiloparsec, then if you put the source at if you put an individual source, for every individual source there will be an exponential cutoff corresponding above the distance in which the cooling time equal to the diffusion time from this distance. Okay, so this means that the following, that above 20 GeV, if the electrons are produced at the spiral arm, the spiral arm is about 20 kiloparsec, is about 1 kiloparsec. If the main source is at 1 kiloparsec, this means that above 20 GeV, the electron will start cooling and will start disappearing because of the effect that I mentioned. On the other hand, the positrons that are secondary are produced uniformly by the protons. And since the positrons are produced uniformly by the protons, they will also suffer cooling, but it will not be as dramatic as this cooling. So this means that above about 20 GeV, if the source is in the galactic arm, then the positron to electron ratio will begin to increase. So very schematically, you have the following picture. This is the supernova at the galactic arm, which is 1 kiloparsec from Earth. Earth is here. And I take now an electron which is about 50 GeV. This electron will diffuse, but as it cools down, it disappears before reaching Earth. On the other hand, if I take now a proton, the proton diffuses, the proton does not care about the cooling. It will produce here a pair, and this pair can reach Earth. So the secondary electrons and positrons form near the Earth and do not suffer so much from the cooling. I mean, they don't care so much, the secondaries, about the distance from the source, because the electrons diffuse and get them nearer to us.
Should we see them isotropical in this case?
There will be some deviation from isotropy, but not significant enough to be tested, because the diffusion length is very small compared to 1 kiloparsec. So there is diffusion at the level of less than 1%. It can be searched for, but it's not something which is dramatic.
So basically what you're saying that above 20 GeV you have only secondary electrons and positrons, yeah?
You begin to switch from, it's not dramatic, it's not sharp.
No, of course it's not sharp.
But you begin to switch from primaries to secondaries, and then there is a second effect. So this is just the first effect. So very dramatically, it's not as sharp as I'm presenting here. You will get something like this. This is the expected positron spectrum. The electron is in red, and the electron, if the source is local, you will begin to see something like this. The positrons are here. They are not affected so much, so you begin to see an increase in this ratio. This is basically what we're saying. Now, the situation is more complicated, and the situation is more complicated because of some coincidence which makes life difficult. The coincidence is the following. The typical estimate of the height of the magnetic field of the galaxy, it's actually not so well known. But the typical estimate is about the height of the magnetic field above the galaxy is about 1 kiloparsec. We are here. This is the spiral arm. It's about also 1 kiloparsec from us. So we have two distances which are of the same order of magnitude. This distance is important because this is the distance which determines the escape of particles from the galaxy. This distance is important because this is the distance of the source of us. Both of them are in the same order, are comparable. So what one has to do is to work out a sort of detailed model of diffusion plus escape, diffusion, and cooling. And one get the following equation that the flux of the electron, as you can see here, should decrease exponentially, depending on the diffusion time divided by the cooling time. So you have your two time scales, and the flux of the electrons, which are produced uniformly of the positrons, which are produced uniformly, should behave differently. But I don't want to go into these details because they are not so important. But it just shows you that the situation is not as simple as I presented here, but it is manageable. I mean, we can understand what is going on. So to see, to check what's going on, we did some very simple Monte Carlo simulation. We have a spiral arm here. The Earth is here. The Sun is here. This is 1 kiloparsec. This is the scale height. This is also 1 kiloparsec, the distance from us. And what we do is we assume that the diffusion goes like e to the minus, like e to the beta. Then the cross section, the cooling goes like e squared, and we just simulate the distribution of the electron. This is the distribution of the electrons. This is the source. This is the spiral arm. This is the distribution around the spiral arm. The Sun is here. This is the escape from the galaxy. But what is the most important is what is most important is this ratio. What is happening to this ratio in this model? So this is the electron spectrum that we find, E cubed times dN by dE, compared to various observations. There is some solar effect here at the lower, below about 7 GeV, with this kind of error bars because of it. So it's not so important, but we can mimic it. What is this is the electron spectrum at about 100 up to 100 GeV, and this is the electron positron positron to electron ratio that we find as compared to the data point. In the meantime, I'll show it in the next slide. The data point is moved slightly, and they all move down. So the agreement with this model is even slightly better.
Hopefully it won't disappear.
What?
Hopefully it won't disappear in the future.
Now, what happens at the higher energies? At higher energies, we had several measurements. First, there were attic measurements which show the peak here around 600 to 800 GeV. As we all heard and you all know, Fermi measurements rule out basically this attic peak here, and we get this spectrum which goes like this. This is by the way the standard uniform model. So the electron, this is the spectrum that we get from Fermi. So what can we say about the higher energies? And this is now superposition of Fermi with Hess. This is the Hess measurement, fit with Fermi. This is the Attic measurement, which are probably wrong. Now, at these energies, this is this is the new Pamela point, which went down a little bit, by about 20%. At very high energies, if you think about what I said before, at very high energies, the sources of the electrons must be very local. Because of the cooling. And to model this, we have done the following thing in the model. This is this part, which I didn't take into account. We have here, by the way, spiral arm supernovas. This supernova, ratio of about, we tried several ratios, it's not very sensitive to it, but of course the ratio should be larger, should be large. We tried 10 to 1 and 5 to 1, both are give reasonable results. I think the 3 to 1 also give reasonable results, but I'm not sure. We cut a hole here of about 200 kiloparsec.
Parsec.
Parsec.
200 parsec, so 200 parsec around the sun. And in this 200 parsec, I was thinking I was going to say 200 megaparsec. The correction was not good enough. So 200 parsec. And in this 200 parsec, we put 5 local sources which are just known to be there of recent supernova, which are both young enough and local enough, so that they are relevant. So we include the contribution of these 5 sources by sort of by hand. We put them in the position that they are, and not surprisingly, people who do pulsar simulations, pulsar modeling, use exactly the same 5 sources because supernovas, remnants, and pulsar are sort of connected. So this is the Miga, monogram, Vela loop, and Sinus loop. These are the supernova that we put in, and we calculate by hand their contribution. So overall, what we have here in the electron spectrum, we have this curve here is the spiral arm electrons. This line here is the electrons from the local 5 sources, and this curve here is the contribution from the disk. So, as you see here, as expected from this model, the contribution from the spiral arm, from the disk, from the spiral arm, which is 1 kiloparsec, drops and completely disappears at about 100 GeV, but other sources, including the contribution, the average contribution from the disk, and the contribution from the local sources, chip in, and when we combine them, we get sort of a flat spectrum here, which is not flat, I mean about e to the 3, which sort of agrees with the Fermi result.
What is the value of beta here for this fit? This diffusion?
The beta that we used was 1/3, which corresponds to Kolmogorov. And I'll remark about this. Well, I can remark about this now. The more standard values that people use are 0.6. When we try to fit Attic, and I will show Attic here, this is when earlier when we were trying to fit Attic, we had to use 1/3 to get to this high peak here. If we life is easier if this peak disappears. We don't have to use 1/3. We can I don't think we can go all the way to 0.6, but it can be larger than 1/3, the beta value that we use.
Why it's sensitive to beta? Why
Why it is sensitive to beta? Because beta tells you the interplay between beta and the cooling, the diffusion and the cooling, tells you how fast you drop here. So if you have a lower value of beta, you drop
But
fast.
you have another parameter which is the ratio of supernova in the arm and in the field, right?
Yes, but you cannot boost it too much. You don't want to go above 10. So this is sort of our best fit now for the data, with local supernovas producing this peak here, and the decrease that Hess is seeing a sharp decrease in the electron spectrum is natural because of the local sources. You have local sources, they cool, and so you expect this decrease. Now, a second thing which has to do with your question about what value of beta that we use. This model that we are doing here is different, I stressed already, from all other attempts to explain this anomaly. All other models says the standard model is correct, we just have to add new source. And this new source is a small perturbation on the overall cosmic ray budget. So it is not, does not affect, so it's a new source which deals just with the problem that we have here, the positron excess. This model says that we have to rethink about the whole issue of cosmic rays from 10 to 1000 GeV, because here they are coming from local source, and we have to take this into account in various ways. So some things which are have to be rechecked. For example, the standard idea that beta is between 0.5 to 0.6, the diffusion coefficient should have stronger dependence on the energy, and other things like the boron to carbon ratio, which has to do with the distance that the protons travel in the galaxy. All these things have to be worked out and rechecked in this model, because on the question like what is the fraction of boron to carbon, what is the boron to carbon ratio, will be also sensitive to the fact that we put the protons at the given source, and most of the protons are coming from 1 kiloparsec from us, and very few protons are coming from very close to us. So this is so situation here is more complicated than other models.
So the standard view is that beta is 0.6, but we're using
the standard view. Well,
the standard number is 0.6.
The standard number is 0.6.
Yes.
As I said, for Attic we had to use 1/3, because for Attic you had to go down very fast and to go up very fast to get it. So you had to use 1/3. With Fermi we can go all the way to 0.5, but we cannot do it with 0.6. But as I said, I'm not so worried, because this understanding that the 0.6 is essential comes in partly from the boron to carbon ratio, and one has to this is one thing that we are doing now. We are trying to redo the boron to carbon ratio estimate with the local model. It does not one thing that we did check, that it does not influence at all the proton spectrum. The proton spectrum remain more or less the same, or exactly the same with all this correction. It does not change. But issue like proton, how far the typical proton travel in the galaxy may change. Yes.
If it means what you can estimate how many pairs you produce to electrons in the cosmic rays, you can say what you have at least 20% in first production when just from diffusion. Leave it. If you have only from secondary flares, it should be 1/2.
If you have only secondaries, it should be 1/2.
Here you have 0.91.
Yes.
It means 1/5.
Actually, it's not 0.1. It's 0. We go to yes. Yes.
Your model.
Yes. 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 Okay.
And it means only 20% comes from a secondary
Yes.
part for electrons. And you can
Yes.
estimate it.
Yes. Yes. Actually, it's a very good point. What you asked me, I'm not sure it's exactly what you're asking, but I'll answer something which may be slightly different. In all other models, or almost all our models, other models, this ratio of positrons keep rising. Because all other models introduce a new source of positrons. So if and the new source, for example, if you take the pulsar model, the pulsar model says that the local pulsars are producing positron pairs. The electrons are decaying, even in this model. Even this is the disk contribution. The disk contribution is going down. The local contribution of positron pairs, positron-electron pairs is increasing. So in all our models, other models, this number should keep increasing. The ratio should keep increasing.
There is an intrinsic, intrinsic cutoff in the source. You cannot produce in pulsars something more than 100,
According to the pulsar model, the local contribution here at about 800 GeV that makes this Fermi spectrum flat is dominated by local pulsars, not by supernova, by local pulsars. If it is dominated by local pulsars and the pulsars produce 50-50 electrons and positron, this means that around here, this ratio should go to about...
But they are suggesting that the pulsar produces TeV electrons?
This is what they are suggesting. I'm not suggesting.
No. It's unlikely. I mean, it's just impossible.
I'm not suggesting it. The
So,
pulsar,
I mean, there will be
the
a
pulsar
constant
model,
source.
the people who suggest the pulsar...
Now, what do they need to produce the results? What do they need in the source?
They need the pulsars will produce about 3 to 5% of the pulsar spin down energy, not.
Yeah, but what energy? What is the energy maximum?
What you need that about 3 to 5% of the spin down energy should go out as pulsar as pairs up to TeV. This is what is needed. If you tell me that it is unlikely, it's not my problem, it's their problem.
Just trying to understand. Up to TeV.
Up to TeV, because this, even the Fermi result, I want to stress, even the Fermi result, I'm almost there. But even the Fermi result, which shows flat spectrum here, needs a local contribution from sources, and in this case it's pulsars. If the positrons here are coming from pulsars, then this is also coming from pulsars, and these pulsars should produce maybe not TeV, but definitely 800 GeV. If you say that
your point was that at what energy this deviation from your model from the other occurs? I mean, you expect a drop in the ratio?
What I expect is the following. What I expect is that here we are still dominated by the spiral arm supernova. As we are dominated by the spiral arm supernova, the electron flux from the spiral arm supernova goes down. The positron flux does not go down. Because of this, in this region, up to about 100 GeV, we expect this value to increase.
100 GeV, that's not
Above 100 GeV in our model, Spiral arm supernova have disappeared completely. What is becoming dominant is contribution from local supernova. These local supernova are not pulsars that produce pairs, but they are regular supernova. And as regular supernova, they produce protons and electrons. Since they produce protons and electrons, this is pure electronic contribution, and therefore, above about 100 MeV, the positron fraction should begin to go down again. So this is what is expected.
So above roughly 200 GeV, you can test it.
Yes, yes, yes. And actually, Pamela was supposed to announce the result of what is going on above 100 GeV in the beginning of May. There was a conference in Rome in which they promised that they will announce the results. The problem, but they didn't. They didn't announce the result. The reason that they didn't announce the result, that they are quite worried. And the worry is the following.
Sorry, so the one below then is positrons and the one above
This is positron. This is the positron ratio.
and the above is electrons.
This is electrons. Yes.
So can I confirm that the positron comes from the nearby source is also included?
Yes, this is the reason that positrons do not come from nearby sources. Protons, our nearby sources never produce directly positrons. The nearby sources produce protons, and the protons produce a secondary positron. This is why you have this peak here, because here nearby protons are producing positrons. The electrons are already decaying very steeply. So here we expect a small bump from local protons producing nearby positrons. All this happening very locally in the nearest 100 parsec.
But how much energy do you need to put in your supernova in the...
This is the standard input.
Standard. And,
about 3%, 3%, which is the standard input, which
and
is...
the number density of the particles is again the standard?
Yes,
I mean,
yes.
because we need, basically, I mean, if you increase the number density of targets, what will happen?
Well, we cannot increase arbitrarily the local
No,
number.
I talk about the violet line.
About here?
Yes, I mean, because you need secondaries. Therefore, it takes both to have a number of primary protons from the supernova,
Yes.
plus to have enough targets on the way, so you can produce efficiently by PP.
The targets on the way is something which, yeah, somehow this number is fairly well measured, because you know how many cosmic rays are in the galaxy, how many protons are in the galaxy, simply from the observation of the cosmic ray flux.
Yes, but this might come from
This may-
I mean, isotopically.
This may come isotopically, but here you modulate it with the ratio of how many sources are in locally in the galactic arm, which we take as 5 to 1. So we say that there are 5 spiral arm supernova per 1 disk supernova. But I was going to answer another question which I was sort of diverted from.
The problem with the Pamela results.
Oh yes, the problem with Pamela result. Now, Pamela is worried, I mean the collaboration is worried, because Fermi came up with their observations, which are which may suffer from systematics, but as we heard 2 days ago, it's very good statistics of this line here. And this line, if you can see on this slope, this is E cubed. So this line is exactly e to the minus 3. And e to the minus 3 plus or minus about 0.01. Now, Pamela measured independently the electron spectrum in this range, 10 to 100, or actually 200 GeV. Their spectrum is e to the minus 3.3 to 3.4. I don't have it here. It's still preliminary, so they don't release it, but they show it in presentations. So there is a discrepancy of about factor of 0.3 in the spectrum of the electrons measured by Fermi and the spectrum of electron measured by Pamela. And the Pamela people are quite worried about this, and because of this they don't publish it yet. They want to understand it, and because of this they also do not publish the positron spectrum, the positron fraction here, which is what I wanted to hear.
Can be a key number to select model. This positron fraction will be a key number to select.
Yeah, this will be the key number here in the whole game. Now, the point is, our point, while I think that everything is compatible with our model, is that if you look at our model, in our model, the electron spectrum is composed of 1, 2, 3 different components. So you don't expect a single power law. We are very happy with wiggles. So it is true that Fermi is consistent with a single slope, but it's not necessarily a single power law. It is just that the single power law is compatible, and it's completely possible that something like this is compatible with the data. And this could resolve the discrepancy if the slope here is, if we break it to several power laws, and so there is nothing. So I think that this is actually a good indication for our model, but we have to wait for the observers to say what they see. So this is our conclusions. That if you take the real distribution, real I mean put the supernovas in the galactic arm, it gives you a correct positron to electron energy behavior. Now, it's not exactly, the break energy is constrained, and it is not a free parameter. I said that the break is at around 10 to 20 GeV. There is no free parameter in determining the break. If somebody would have come with this model, with the same observations, and the Pamela break was at 50 GeV, there is no way that we could fit the data. So the break is just where it should be. To see what is going in at higher energy, we have to take the local supernovas. And we have two predictions. One, which I mentioned, that the ratio should saturate at much less than 50%. Actually, it should saturate at about 15% and then go down above 100 GeV. And the energy should decrease because of fresh electrons which are coming from the local supernova, which are causing this fraction to decrease. So this is the story, and this is the end of the talk, but the question mark is this is the end of the story. I'm not sure.
Thank you, Tzvi.